Okay, so let's get started. So just a reminder, I know that last week was reading break, so you didn't have to do a quiz. You might have forgot about these things called quizzes, right? The ninth quiz is due tonight. There's also, I put an announcement on Brightspace about this. It's not mandatory, but if you do want to give feedback on the course, there's course experience surveys. It's kind of a good way to give feedback, and it helps us make the course better in future. It probably isn't going to help you because the course is almost done, but it will help future students if we can make the course better. And maybe it helps you because you can vent, if you're very frustrated with how this course went, you can vent your frustrations there. Okay, so we're going to do some more Markov chain stuff. So here's an example. So what I'm going to do now is give you a word problem and get you to turn it into a Markov chain problem, or like turn it into a Markov chain. So let's say Joseph eats lunch at either Mystic Market or Felicitas each day of the term. Okay. And here's how it's going to work. So for whatever reason, he makes his decisions in a random way. On the first day of the term, he just flips a coin. So the first day, he flips a coin to decide where to go. Okay, so heads, Mystic Market, tails, the pub. After that, though, he's going to do something a bit different. So each day he goes to Mystic Market. He has a 75% chance of going to Felicitas the next day. And on the other hand, so each day he goes to Felicitas. In case you don't know what Felicitas is, it's the pub on campus. So he has a 80% chance to go to Mystic Market, so to go to Mystic the next day. Okay. And all I really want to do at this point is, to determine the initial state vector, initial state matrix, I mean. So initial state matrix and transition matrix of this Markov chain. Okay. Okay, so even for a fairly simple question, these get quite long. So hopefully it's kind of clear that this is going to be a two-state Markov chain. Right, and the two states just represent the two different places where he might have lunch. So one state is, so kind of my two states are mystic or Felicitas. Okay. And let's say we're gonna, in all of the matrices, we're gonna represent the states in this order. So like this is state 1, and that's state 2. Right, mystic is state 1, Felicitas is state 2. You just have to, it doesn't really matter which way you represent your states. You can do it either way. You just have to be consistent when you're doing it and not get confused. So can anyone see from this problem what your initial state matrix is going to be? Yeah. How come? Yeah, exactly. So, and that's what that's the kind of information you should be looking for here is, how does the process start out? And what we're told is the first step, before the process starts, we have a 50% chance. So yeah, like you said, on the first day, he just flips a coin, 50-50. So that's our initial state. So that's how you should kind of think of these things. Like before you even start the process, you've got this chance of being in either of the two states. Okay. And now your transition matrix. So by the way, the initial state matrix, we always write it as S0, S0. And the transition matrix, we write as P. Can anyone tell me the first row of this matrix? I think I know that you know. Any other thoughts about the, yeah? Sounds right to me, yeah. Right, because this row corresponds to the previous day being Mystic Market. And then you want to say, if the previous day was Mystic Market, what are the probabilities of the next day? And it's 0.25 that he's going to go to Mystic Market again, and 0.75 that he's going to switch. So so you should think of this column represents Mystic Market. This row represents Mystic Market. This one represents Felicitas. So yeah, then this row is going to be kind of similar, except it's 0.8 and 0.2. So like this 0.8 represents the probability of going from the state Felicitas to the state Mystic Market, right? Okay. Any questions about that? Okay, so this is just generally how you would take a word problem and turn it into a Markov chain. Let's now do so I'm going to write down a different Markov chain and we're going to analyze it in various ways. So let's say, yeah, 3 runners. So I'm gonna pick these names so that we can call them A, B, and C. So Aaron, Beth, and Candace, which we can kind of represent as A, B, and C, right? So they race each other every week. Okay. And they're not like the same speed, but they're pretty close. So like basically anyone can win this race with some probability. And the winner, it changes each week. So the winner changes each week. According to a, so randomly, according to a Markov chain with the following transition matrix. So I'll call it P. Okay, so it's going to be first row is 0.2, 0.2, 0.6. Then we've got 0.3, 0.5, 0.2, 0.5, 0.4, 0.1. Okay, and we're going to think of this as, you know, the states are ordered A, B, C, corresponding to Aaron wins, or Beth wins, or Candace wins. Okay. So we're not told here what the initial state is at the moment. We're just told whoever wins this week, this is how the transition probabilities are going to go. So if Aaron wins, then the probability he wins next week again is going to be 0.2. The probability Candace wins would be 0.6. Okay. Any questions about this example? I mean, I haven't asked you to do anything yet, but. Okay, so I'm going to build up some different kind of questions of increasing difficulty here. So first question, let's say, so if Candace won this week, then what is the probability that Beth wins next week? So this is just kind of checking your comprehension of what this matrix means, really. So any thoughts? Yeah? Yeah, I think so, yeah. So exactly, and you can get that by, yeah, so you're on the row for Candace, and you want to look at the column for Beth, and you're right, it's exactly 0.4. So 0.4, because it's on, well, it's like P3, 2, like meaning the entry on the third row second column. Right, okay, so I mean, if you were doing this and you just wrote 0.4, that's the main, that's the answer, yeah. Yep. So that's just kind of interpreting what this matrix means. So in this row, this row means we're assuming Candace won this week. So we're on the row for C. And then these probabilities are like, if Candace won this week, this is the probability Aaron wins next week, the probability Beth wins next week, and the probability Candace wins next week. So what this is asking is just for that actual value. So given that Candace won this week, what's the probability Beth wins next week? Actually, what we're going to see, each question I give you here, I'm going to solve it in a few different ways. And we'll see that there are faster ways and slower ways to do these things. So this was the fastest way. Just read it right off the matrix. But you could also say, if you didn't notice this, that you could do it this way, you could also do it another way. You could say, okay, what does it mean for Candace to win this week? It means the initial state is this. So just to be clear, this is a perfectly fine solution. You can just write this down. But just to kind of show you, there's more than one way to do this. Right, so this initial state vector means, like, we're assuming Candace won, which means Candace won with probability 1, right? And then you could take S0 times P, right, which would be, so it's 0, 0, 1 times the first column, which is just 0, 0, and then 0.5. Actually, if you think of the pattern here, this is always just going to take, for each column, it picks 0 times the first, 0 times the second, and then just writes down the third, 1 times the third number. So basically, this is just giving you the third row here. So this is saying, so another way you could do it is by saying, okay, my initial state was this. I do one step of the process, and it tells me that the probability Beth wins the next time is 0.4, right? So you can also get the 0.4 from here. It is doing the same thing. Any questions about that? Yeah. For this one here, or this was given in the question. Yeah. Yeah, so you didn't have to work that out. Any other questions? Okay, so this would be like a slightly longer way to do it because you have to do a bit of matrix multiplication, but it's not that bad. Okay, let's do a little bit harder question. Well, okay, here's kind of a reverse question. So what does the entry on the third row and second column, not of the matrix P, but of the matrix P squared, represent? So P squared is the matrix P times P, doing matrix multiplication. This is we haven't really talked about this, so if this seems tough, that's probably why. Any guesses? Yeah? It's not quite that, but you know, definitely. I guess you're getting the 2 is coming in there somewhere. Yeah, it's not quite. It's something a little bit. Any other thoughts? So what this is going to represent, it turns out, is if we assume Beth wins this week, this will tell me the probability that. Or sorry, if we assume that Candace wins this week, then the entry on the third row and second column of P squared will tell me the probability that Beth wins 2 weeks in the future. So not the probability that she wins next week, but the probability she wins the week after that. So the answer here would be, the probability that Beth wins in 2 weeks, given that Candace won this week. Okay. So that wasn't exactly a fair question because I've never told you how to do this. Yeah. Those would be different, yeah. And basically this entry in that matrix is it's gonna take into account all the different possible ways this could happen. So this will take in the probability of like, so assuming Candace won this week, this will include the probability that, let's say Aaron wins next week and then Beth, or Beth wins next week and then Beth wins again, or Candace wins next week and then Beth wins. So it takes into account all the different possibilities. And yeah, those different things have different probabilities. It is true, yeah. So generally speaking, if you take a power of the transition matrix and you look at some row and column, it tells you the probability of starting in the state corresponding to that row and ending up in the state for that column after n steps if you're taking p to the n. I mean, actually, you can think of this like this here. Here we were talking about what's in the third row, second column of P, right? That's the probability Beth wins given that Candace won this week. P is the same as P to the 1. So like this is like the same as after one step, what's the probability it changes from Candace to Beth? The entry in P to the n would be in n steps, what's the probability it changes from Candace to Beth? Okay, that was a bit of a trickier one. Okay, so the next thing I want to do is let's compute this value. So compute the probability that Beth wins in 2 weeks, given that Candace won. I don't know if Candace is with an I or an A. Maybe it's both, but today, or this week. Okay, so like we said in part B, we said this should be the entry on the third row. So what we want to do is compute the entry on third row and second column of P squared. Okay. Here's one way you might want to do that. I mean, if you want to know an entry of P squared, one way you could do that is just compute the whole, so kind of, I guess, method 1. If you really wanted to, you could compute P squared. But if you think about it, that might be kind of wasting your time a little bit, right? Because you don't need to know, P squared is going to have 9 entries. You don't need to know all 9 of them. You just need to know one specific entry. So you could compute p squared, but completely, but I would say it's not, I wouldn't recommend it. What if I just want the entry on the third row and second column? Can anyone see how I could get that? Well, when I multiply two matrices and I want to know what's on the third row and second column of the product of those matrices, what I do is I multiply the third row of the first matrix by the second column of the other matrix. So I just have to do this one matrix multiplication, and that should be good enough, right? If I want to know what's on the third row, second column, I just multiply the third row of P by the second column of P. So I guess the second method, so I just take the third row times the second column of P, right? So if I take 0.5, 0.4, 0.1 times 0.2, 0.5, 0.4. Oh. Yeah, okay, it looks like my matrix changed as I went to different pages of my notes. But okay, you could compute this, right? This is going to be 0.25, sorry, no, 0.1. So 0.5 times 0.2 plus 0.4, 0.5 plus 0.1, 0.4, which is 0.1 plus 0.2 plus 0.04. Something like that. Right, and so this should be your answer. So that's a probability. If Candace won this week, that's a probability Beth will win the week after next week. Okay. Okay. Any questions about any of this at the moment? So hopefully you can see that this is faster than what it would have taken you to compute the entirety of p squared, because you'd have to do 9 of these calculations, and we just had to do 1 of them. I guess a third method, which is probably better than the first one, but not quite as good as the second one, is you could just, again, just like we did over there, you could start with the initial state being Candace wins, and then find S2, right, which is S0 P squared, right? Or in other words, it's S1 times P, where S1 is S0 times P. So like, to go from S0 to S1 is not too hard, and then from S1 to S2 is not too hard. So that would be another way to do it. And then once you found S2, then you just look at the second entry, and that's the probability Beth wins in 2 weeks, right? Any questions about this? Yeah. It's not skipping anything. Like what's going to end up happening here? Like, so it's this one we're talking about, right? The third one? Yeah, so basically you're going to have to do what we did here. So actually we already did part of this calculation already. So when you have S0 being this, S1 will be this matrix. And then I just need to do this matrix times P. And then, actually, if you could think about it, it's going to do the same thing as here, right? Because when I do this matrix times P, it's okay, it's going to do 3 different calculations, but one of them is going to give me this value. Yeah. I don't know if that helped or not, but okay, not particularly. But basically the idea here is we're asking what's the probability Beth wins in 2 weeks, given this initial state. So you start with this initial state, you multiply by the transition matrix twice, and that'll give you the probability of being in any possible state after 2 weeks. Okay. So let's so all of these questions, again, they could have been done with a tree diagram. But let's ask a more interesting question now, okay? So imagine that they race each other, you know, a really large number of times. Let's say, you know, infinitely many times, whatever that means. Or if you don't like infinitely many times, just think they race each other 1 billion times, or you know, a really large number of times. Who wins most often? Out of these 3 people. So not only who wins most often, but, well, here's another question. Does the initial state matter? Okay. So actually, maybe let's have a vote on this. I can tell you it's probably not easy to just see from this matrix, but actually maybe I'll just tell you the answer to the second question first. So it doesn't actually matter the initial state does not matter. In this case. So no matter who wins if I say Aaron wins the first week, or Beth or Candace, or all 3 of them have equal chance, or whatever, no matter what the first week is, it doesn't matter. Whoever wins the most often will still win the most often. It doesn't matter about the initial state. But I guess if you had to vote, does anyone have a feeling of which? So maybe I'll give you a second to look at this matrix. And then let's vote. I'll go A, B, and C, and you can raise your hand. So who thinks that Aaron wins, in the long run, wins the most? Who thinks that Beth wins the most? And who thinks that Candace wins the most? Huh. There's quite a good consensus there. All consolidating around the right answer. I don't know how you knew that. But you're right. There must be some intuition that you guys have. Yeah. So this column is like the kind of the heaviest column in some sense, right? That makes sense. Yeah. That turns out to be the right intuition. Do the rest of you have that intuition that just this column, this column adds up to a little bit more than 1. It's like 1.1. This column adds up to 1. That one adds up to 0.9. So it does seem like, yeah, whoever wins the previous round, there's a little bit higher chance that it's going to go to Beth next, because that column is quite heavy. So yeah, that's very good intuition. That's the right answer. Oh, sorry? On the question, you actually probably wouldn't get a question that's this, like just asking for this much information. It would say something more detailed, which is, if you run this process forever, what percentage of the time does Beth win? And then that becomes more tricky to answer. But the intuition, when you compute these 3 percentages, it's going to go exactly with your intuition. That'll be the highest percent. That'll be second highest. That'll be the lowest. But getting the right number is the hard part. Okay, so let's, I'll start kind of introducing this, but we'll continue this next time. So to answer questions like this, like kind of rigorously, without just your intuition, we need to talk about something called regular Markov chains. So it turns out that like not all Markov chains, like this question, when we're talking about, suppose this goes infinitely many times, who wins the most, or like what state is it in the most or something, or specifically what percentage of the time is it in every state? Like these questions are a bit, these questions don't always make a lot of sense in some sense. However, when you have a regular Markov chain, these questions have a good sort of meaning. So what is a regular Markov chain? So a Markov chain is regular if there exists an integer n such that all entries of p to the n are positive. Okay. So in this example, this Markov chain is definitely regular because, p to the 1, just p itself has all positive entries. So this is a regular Markov chain. But it could be the case that you might have a Markov chain where some of the entries are 0, and when you square it, you get all positive entries. Or it could be the case that you've got some zeros, you take the square, you still have some zeros, you take the cube, the 4th power, the 5th power, and then finally you don't have any zeros. That would be a bit evil to give you that kind of question, right? Because you don't want to compute the 5th power of something, but it could happen. So for a regular Markov chain, the long-term behavior is given by something called the stationary distribution. Okay, which is a matrix, let's say S, which is S1, S2 up to Sk. So here I'm assuming there are k states. For example, over here there's 3 states, so this would just be S1, S2, S3. Such that if so 2 things happen. So it has to be the values have to add up to 1 because we want to think of these values as being probabilities. So probabilities always have to add up to 1. And it has the property that S times P equals S. So in the long run, basically what these values represent, so if you have so just to back up, if there's a matrix S, which has this property that the values add up to 1 and S times P equals S, then those values tell you the long run probabilities. So in the long run, the amount of time spent in state I is, or I guess I should say the proportion of time spent in state I is Si. Okay. So if we wanted to determine the percentage of times that Beth wins in the long run, what we would do is we want to find a matrix S such that S times P equals S. And then we look at the second entry of that, and that value will be like 0 point something, and that tells us the percentage that Beth wins in the long run.